This course is designed to give you an understanding of the basic concept of manipulating force through a hydraulic system using pressure control valves. The two basic design types of these valves are direct acting and pilot operated.
The primary concern in fluid power circuits is to either control the rate of flow or the pressure level. One misconception has been that pressure may be controlled with an orifice or flow control device. This is never accomplished with any degree of accuracy. For accurate control of force, 6 types of pressure controls have been developed. They are relief valve, unloading valve, sequence valve, reducing valve, counterbalance valve, and brake valve. By symbol, these valves closely resemble one another. Often, only their location in the hydraulic circuit will designate what type of pressure valve they are. Maximum system pressure can be controlled with the use of a normally closed pressure valve. With the primary port of the valve connected to a system pressure and the secondary port connected to tank, the poppet is actuated by a predetermined pressure level, at which point primary and secondary passages are connected and flow is diverted to the tank. This type of pressure control is known as a relief valve. A direct-acting relief valve is one in which the poppet is held closed by direct force of a mechanical spring, which is usually adjustable. Spring tension is set on the knob to keep the poppet closed until system pressure working against the poppet reaches the desired cracking pressure. When the system pressure reaches full relief value, all fluid is passed across the poppet to the tank passage. It should be noted that direct-acting relief valves are usually available in only relatively small sizes because it is difficult to design a strong enough spring to keep the poppet closed at high pressure and high flow. Pilot-operated relief valves are designed to accommodate higher pressures with higher flows being confined to smaller frame size than a direct-acting relief valve with the same rated flow capacity. The valve is built in 2 stages. The second stage includes the main spool, held in a normally closed position by a light, non-adjustable spring. The second stage is large enough to handle the maximum flow rating of the valve. The first stage is a small direct-acting relief valve, usually mounted as a crosshead on the main valve body, and includes a poppet, spring, and adjustable knob. The second stage handles full rated flow to the tank. The first stage controls and limits pilot pressure level in the main chamber. Relieving action through the main spool is as follows. As long as the system pressure is less than relieving pressure set on the control knob, pressure in the main spring chamber is the same as pump line pressure because there is no flow through the control orifice, and consequently there is no pressure drop from one side of the orifice to the other. When pump line pressure rises higher than the adjustment set on the control knob, the pilot relief poppet moves off its seat. This starts oil flow from the pump line through the orifice, across the pilot relief poppet, and to the tank. This restricted flow caused by the orifice creates a pressure difference between the pump line and the area across the pilot orifice. This pressure imbalance causes the main poppet to move off its seat. This will discharge enough of the pump flow to prevent any further rise in the pump line pressure. When pump line pressure drops below the control knob setting, the pilot relief closes, flow through the orifice ceases, and the main spring can reseat the main poppet. The pilot-operated pressure relief valve comprises a valve body, a main spool cartridge, and a pilot valve with a pressure setting adjustment. The pressure present in the primary port acts on the bottom of the main spool, and at the same time the pressure is fed to the spring-loaded side of the main spool via the control lines and containing orifices. The pressure is also present at the ball of the pilot valve. If the pressure increases to a level above the spring setting of the pilot valve, the ball opens against the spring. The pilot oil on the spring side of the main spool cartridge now flows into the spring chamber of the pilot valve and is directed internally to the secondary port and back to the tank. Due to the orifices in the control line between the primary port and the pilot valve, a pressure drop or pressure differential exists between the bottom of the main spool and the spring side of the main spool. This pressure differential lifts the main spool off its seat and connects the primary pressure port of the valve to the secondary or tank port. Fluid now flows to the tank, maintaining the set operating pressure of the valve. A sequence valve is a normally closed pressure control valve that ensures that one operation will occur before another based on pressure. In our clamp and drill system, we want the clamp cylinder to extend completely before the drill cylinder extends. To accomplish this, we place a sequence valve just before the drill cylinder. We set the valve to 500 psi. This will ensure that the drill will not extend before we have reached 500 psi on the clamp cylinder. Notice that once the drill cylinder has extended, pressure will continue to rise to the system relief setting of 1500 psi. A pressure-reducing valve is a normally open pressure control valve used to limit pressure in one or more legs of a hydraulic circuit. Reduced pressure results in a reduced force being generated. A pressure-reducing valve is the only pressure control valve that is normally open. A normally open pressure control valve has primary and secondary passages connected. Pressure at the bottom of the spool is sensed from the pilot line, which is connected to the secondary port. Remember, a pressure-reducing valve is normally open. Now, let's place our pressure-reducing valve in an actual circuit to see its application. The illustrated clamp circuit requires that clamp cylinder B apply a lesser force than clamp cylinder A. A pressure-reducing valve placed just before the clamp cylinder B will allow flow to go to the cylinder until pressure reaches the setting of the valve. At this point, the valve begins to close off, limiting any further buildup of pressure. As fluid bleeds to the tank through the valve drain passage, pressure will begin to decay off and the valve will again open. The result is a reduced modulated pressure equal to the setting of the valve. A counterbalance valve is a normally closed pressure valve used with cylinders to counter a weight or potentially overrunning load. In this circuit, without a counterbalance valve, the load would fall uncontrolled or overrun, and pump flow would not be able to keep up. To avoid the uncontrolled operation, we place a counterbalance valve just after the cylinder. The pressure setting of the counterbalance valve is set slightly above the load-induced pressure of 1000 psi. This counters the load. As we extend the cylinder, pressure must slightly rise to drive the load down. Now that you understand the application of a counterbalance valve, push the extend and retract buttons to watch the function of the valve. A brake valve is a normally closed pressure control valve with both direct and remote pilots connected simultaneously for its operation. This valve is frequently used with hydraulic motors for dynamic braking. Because any downstream resistance will add to the load on the hydraulic motor, we pilot remotely using working pressure to keep the valve open during running. This eliminates back pressure on the motor. When we de-energize the directional valve, remote pilot pressure is lost, allowing the valve to close. The inertia of the load will now drive the valve open via the internal pilot, giving us dynamic braking. Now that you understand the application of a brake valve, push Energize, then stop to see the valve function. An unloading valve is a remotely piloted, normally closed pressure control valve that directs flow to the tank when the pressure at that location reaches a predetermined level. A high-low system is a good example of an unloading valve application. This system may consist of two pumps, one being a high-volume pump and the other being a low-volume pump. As the cylinder approaches the load, the pressure requirement is low. If the pressure requirement is below the unloading valve setting, both pumps work together to provide a rapid approach to the load. At this point, the system pressure increases, thereby opening the unloading valve. The flow from the high-volume pump is directed back to the tank at a minimal pressure. The low-volume pump continues to deliver flow for the higher pressure requirement of the work cycle. Once the flow from the high-volume pump is unloaded, both pumps join once again for a rapid return of the cylinder. The high-low system requires less input power to meet the work cycle's speed and force requirements. Now that you understand the application of the unloading valve, push the extend or the retract button to watch the function of the valve.